So we are in section 12.1 still. This is our second part, part B. And we're going to look at some other multivariable functions that don't graph as planes. We saw with planes, every single time we had the equation of a plane, we always had something times x to the first, plus something times y to the first, plus something times z to the first. So x, y, and z all being to the first power is sort of the hallmark of a plane. We're going to start looking at other powers of x and y, and the ones we're going to look at in this section are called cylinders. Now the first thing you need to do is kind of get the whole old tin can version of the cylinder out of your head, because in math, the word cylinder is much more general than just that typical round sort of tin can look. It's only one of many shapes that mathematicians will call a cylinder. Here's the mathematical definition of a cylinder. It's the three-dimensional graph of an equation that contains only two of the three possible variables. So we'll graph in 3 dimensions, but only 2 of the 3 variables will be in our equation. So equation of a cylinder contains 2 variables. If I were to graph that equation in just 2 dimensions, it'll be what's called the cross-section of the cylinder. And then we generate the 3-dimensional graph, which looks like the cross-section, if you can imagine kind of pulling it along, parallel to the axis of the missing variable. Hopefully that will make a lot more sense after we actually graph a few of these. So let's start with this one. I want to graph in 3 dimensions. So my first cylinder, x squared plus y squared equals 9, you'll notice contains only 2 of the 3 variables. The 2-dimensional cross-section here is just, you can see a circle of radius 3 in the xy plane. What I want to do now is I want to graph that 3-dimensionally, and then I'm going to pull it in the direction of the z-axis, because z is our missing variable. All right, so let's give that a try. I'm going to take my circle of radius 3 in the xy plane and translate it over here to my 3-dimensional graph. So I would have x and y intercepts of plus and minus 3. Right. Looks a little oval because of the perspective, the xy plane is laying flat, right? It's not up and down. All right, imagine taking that circle and pulling it up and also down, parallel to the z-axis. Can you see that this is going to generate kind of that classic cylinder that sort of looks like a tin can? What I usually do when I draw these is I show kind of that pull. I'm going to show up, and then I kind of repeat my circle shape here on the top. Now it would go down as well, but you can add too much to a graph until you get to the point that you can't even see what it looks like anymore. So I'm going to leave it at that. There is my 3-dimensional cylinder. Technically it would go up to get forever, and it would also go down forever. By the way, caveat, I'm not the best 3-dimensional drawer in the world, so I'm going to apologize for the fact that my pictures may not be wonderful. We'll be graphing a bit on Maple later, and of course, they always have better pictures than what we can draw. All right, let's try a second one. This one's not going to look like your classic tin can shaped cylinder. We have z equals y squared. So first of all, again, I'm going to do the 2-dimensional cross section. It's in the YZ plane. And it's just a parabola, right? Z equals y squared would essentially look like this. Now I have to imagine taking that and pulling it in the direction or parallel to the x-axis, because x is the missing variable. It's not included in the equation. So this one's fairly easy to translate over into my three-dimensional graph. Y and z nicely are the flat plane of the paper. So I'll just go ahead and do that. Like so. There's my parabola. And then I have to imagine pulling that forward in the direction of the x-axis, just like when we drew before. Keeping lines parallel really helps a lot. So I'm going to draw another copy of the parabola forward here somewhere on the x-axis. I'm going to try and make this so I can draw a parallel line to the x-axis up here on the top. And actually I'm going to bring this one down first, like so. And if I shade this in a little bit, might kind of help me see. This is kind of that sort of an upside down tunnel shape, so to speak. And that's called a cylinder, even though it doesn't look like sort of our classic geometry definition of a cylinder. All right, we're going to do one more and then we'll take a look at maple. In this last one, I want to graph x equals e to the z power. Again, just two variables, so I know it's definitely going to be a cylinder. And I'm going to start with my two-dimensional cross-section. Now, x equals e to the z is actually easier for me to think of. I like to think of z as my dependent variable. My head works better that way. So I'm going to rewrite this as z equals ln x. And most of us probably know what the natural log graph looks like. If not, it's easy enough to quickly generate it on the calculator, right? You could do y equals ln x and then just replace it. But z equals ln x should look something like that. Kind of classic natural log graph. X-intercept is 1. All right, that I'm going to have to translate to my three-dimensional graph. And then I'm going to have to pull that, in this case parallel to the y-axis, since y is the missing variable. All right, this one I have to be really careful when I translate. I know the x-intercept is going to be 1, so that's here. And then notice that it's going to go down along the negative z-axis. It kind of goes down here. And then as z increases, it comes out over the x-axis. So it kind of does that. Right? Looks a little different with the changed perspective of the xz plane kind of coming out toward us. All right, same deal. I need to now imagine this pulling this parallel to the y-axis. And that means I need another copy of this over here, parallel to the y-axis. So I'm going to put this x equals 1 kind of here. And then I'm going to say this would have to come down like this. Draw a line parallel to the y-axis to kind of level that off. And then it kind of comes up and out. Draw that line, and I can kind of top this off. And there you've got that three-dimensional cylinder parallel to the y-axis. All right, let's take a quick look at what Maple tells us here, because it can draw better than I can, for sure. I've again got them pre-typed in, so you don't have to watch me type. But here we go. Once again, it's going to be an implicit plot 3D. Don't be fooled by the fact that there are only two variables. If you want a three-dimensional graph, you have to include that 3D in the command. So here's our first one. The x squared plus y squared equals 9. I've set up a little window for my x, y, and z. And you can see over here, it's just what we graphed, right? I've got the sort of classic tin can cylinder shape. If I want to, I could even add an axis equals normal here. And then you can really see that z-axis coming right up through the center of the cylinder. Again, remember, you can play with the style. If I want to do style equals surface, I won't see the grid lines now. It'll just look like more of a smooth cylinder. Or you can use num points to get a grid, but less of a grid. All right, here's our second one, Implicit Plot 3D, and here's that z equals y squared, right? The one that turned out to be the parabola pulled parallel to the x-axis. And let's see, move that around so you can kind of see it. Again, if I wanted to, I could put in axis equals normal. If you really wanted to see how that is right along the x-axis, right? The x-axis is right down here. It forms the bottom of my cylinder. And I won't take your time to do it now, but again, you could play around with style and num points and all that good stuff. And here's the last one, which was the hardest one for me to draw. Here's the x equals e to the z. Again, I've set my grid. And you can see that same sort of thing happening here. If I wanted to do axis equals normal, so I can actually see that y-axis, there it is. You can see here we are, here's the y-axis, and that's just exactly parallel to the y-axis as it comes out over the x-axis here. All right, so that's cylinders as three-dimensional graphs. Again, you recognize them because of the fact that the equation will only have two of the three variables when you see it.